In this video, I'm going to talk about the basic reproductive number, or R0. So the basic reproductive number is the number of expected secondary cases. So that's the number of expected people that someone who is infected and contagious will go on to infect, basically. So let's just say a disease has an R0 of 3. That basically means that for each infected person, they're likely to go on to infect 3 other people. So the calculation of R0 is R0 equals CPD. So just going over these individually, C is the contact rate, P is the transmission probability, and D is the duration of contagiousness. So contact rate, C, is the average number of contacts that an infected person has with others, and that has units of per time, or I guess contacts per time. So what that might look like is 5 contacts per week. And yeah, something you got to watch out for here is that C has units of time, and so does D, the duration of contagiousness. And sometimes those are given to you in different units, like C might be in contacts per week, and D might be in days, or something like that. So yeah, that's one thing you got to watch out for. P is transmission probability, and that's the probability a susceptible person develops the disease following one contact. And that doesn't necessarily need to be from person to person. It can also be from any infectious reservoir. So the amount of contacts you're having with like poorly cooked food or contacts with an infected animal. So transmission probability, it's going to vary from basically by the nature of the pathogen. Pathogens have different infectivity, or that might not be the right term, the different contagiousness. Yeah, so this is an example where like chickenpox is definitely going to be more contagious than HPV. And even within pathogens, depending on the way in which you're exposed, it might have a high transmission probability or a low transmission probability. So if we're looking at a blood-borne illness, something like HIV, the same pathogen can have very different transmission probabilities in 2 different scenarios. So just think of the amount of infected blood that you're coming into contact with a blood transfusion versus a contaminated needle, like sharing needle for injection drug use. The amount of contaminated blood you're coming into contact with is much larger for a blood transfusion. So for the same pathogen, it's going to have a much larger transmission probability. This is an example from my video on the component cause model. So this is just an example from like I used to go to University of Guelph, and that's like an agricultural university. So this is an example from there about mastitis. That's just like an infection of the udder that dairy cattle get. Whether a cow becomes infected following like one exposure is going to be the combination of so many things. Basically, you can break those down into host factors, like how strong the immune system of the host is, and that's a product of a bunch of things, like whether they've had the disease before, how old they are, and just basically how immunocompetent they are, which is a combination of how good their diet is and stuff. The agent on its own, different agents can produce the same disease to varying like infectiveness. Basically, and the agent and environment can also interact in several ways. That's basically the reason that things like the common cold are seasonal. And yeah, what I'm getting at here is again, it's such a heroic assumption to be able to say that transmission probability is this constant thing. It's gonna basically, I would imagine like literally every situation, like every contact has a different transmission probability, just because of how different the situation will be from time to time. But yeah, basically for the case of calculating R0, it's basically considered to be this constant thing. So when working with binomial probabilities, you might have also seen this kind of thing with P's and Q's when you're doing like population genetics, things like Hardy-Weinberg equilibrium. Yeah, so P, probability of transmission following one contact. Q is just the complement of that. It's the probability of non-transmission, so 1 minus P. And what we can use this to do is find the probability of transmission following several contacts. So P equals 1 minus Qn. Just forgetting the 1 minus part, just looking at why we're why we're doing Q to the N. So Q is the probability of not getting the disease. So let's just say each contact is flipping a coin, and each time the coin's flipped, you have a 0.5 probability of surviving it, not getting the disease. Let's just say it's deadly, I guess, for the sake of the example, like it's a Russian roulette kind of thing. So if you flip the coin twice, your probability of of surviving both times is 0.5 times 0.5, so 0.25. So the more times you undergo this exposure, that kind of probability compounds and gets smaller and smaller. You just keep multiplying 0.5 together. And then, yeah, basically, like, the complement of that, it's just 1 minus that kind of collective probability for multiple exposures. And basically that probability of transmission is going to get higher and higher, because as N goes up, Q gets smaller and smaller. So here's just an example. If HIV is a transmission probability following contact with a contaminated needle of 0.0008, what's the transmission probability following 200 exposures, so 200 injections with a contaminated needle? So just pulling information from this, we have a P of 0.0008 and an N of 200. We can find Q, just the complement of P, 0.9992. And after 200 exposures, that Q is going to get very small. So we end up with 0.15 as our P. So what this is driving home is, for one contact with a contaminated needle, that's like a 0.08% transmission rate, but with 200 contacts, which is a surprisingly reasonable number through the course of someone's addiction to opioids, it goes up to 15%. So that adds up pretty quickly. And I've talked about this a little bit throughout. There's some issues with these calculations of transmission probabilities because they rely on some really heroic assumptions. So as soon as we're talking about infectious disease, the contacts are almost never independent, and cases are almost never independent. But you would have to make that assumption that all contacts are independent, and the probability of transmitting the disease is the same from contact to contact, which is obviously a heroic assumption just because of, I thought it was going to be on the next slide, but back to that mastitis example, there's all these host-specific factors that even the same infected individual contacting two people on the same day, the susceptibility of those hosts is going to differ greatly. So this is a much more resistant equation that is more resistant to some of those assumptions I just talked about. And this is an incidence rate calculation where incidence rate equals PCP. So the first lowercase p is transmission probability as we've been using it. C is contact rate, like we've been saying, and P is the prevalence at the time. T, like prevalence of the illness. So that's taking into account the amount of people that are susceptible. So this one is pretty resistant to changing situations because a lot of the other equations don't take into account the amount of susceptible people. They generally assume everyone is susceptible. But this is one that will work where, since C is involved, if you have the other information, you might be able to get since P is involved, if you have all the other info, you might be able to solve for P. So duration of contagiousness, that's pretty understandable. It's just the number of days or weeks or whatever your unit is that you're capable of transmitting the infection. And that's necessary because of the units of C, just because it's contacts per time. You need to close the gap as far as getting time elsewhere in that equation. So yeah, our reproductive number is unitless. Yeah, it's unitless, just because for C you have time in the denominator, P is unitless, it's a probability, and D has time in the numerator, so you end up with, actually no, it's not unitless, R naught's just a count, sorry. So the number of people that you infect as a yeah, we already talked about that. Sorry. So just calculating R naught, if the average duration of contagiousness is 10 days and transmission probability is 0.02, and there's 2 contacts per day, what is R naught? So pulling C out of the equation, 2 contacts per day, P, transmission probability of 0.02, and 10 days of contagiousness. This is a pretty easy one, but basically like some of those tricks that I put in earlier about calculating P first and having different units of C and P, that's where you can get tripped up, but overall these are pretty easy calculations. So as far as interpreting what some of these, what R naught values mean, basically, an R naught of less than 1 is a self-limiting situation where contagious people infect less than one other person. And this is an image from my video on that was differentiating incidence and prevalence. And this is a situation where, I guess, yeah, so the cup pouring into the funnel is incident cases, and the amount coming at the bottom of the funnel is recoveries and deaths. And depending on basically how big the bottom of the funnel is and how fast you're pouring in, that'll dictate the amount that's in the funnel at the time, which is the prevalence. It's a pretty common example that people give. Sometimes they'll use like a bathtub or something. But yeah, so this is a situation where infected people are recovering faster or dying faster than new cases are coming on the scene. So this is an example of a disease that's, or like, I guess, you can't even call it an epidemic, like a outbreak or whatever, that's going to self-limit itself. R naught equals 1 is equilibrium, so that's when contagious people infect on average one other person. And this is a situation where the cup is pouring water in at the exact rate that it's coming out the bottom, and the amount that's in the funnel is going to remain constant, and basically individuals are replacing themselves in the disease population. And R naught above 1 is an epidemic, so that's a situation where contagious people infect more than one other person, and that's where the cup is pouring faster than it's coming out the bottom, and yeah, that's the definition of an epidemic. So just looking at this R naught equation, it kind of shows you just some of the ways that epidemiologists think, where you can look at these different components of the equation and see them as different ways that you can reach the same goal. So if your goal is to reduce R naught, you can look at C, P, and D as 3 separate ways to go about that. So you can reduce the frequency of contacts. We did that with COVID by making people stay inside. You can reduce the transmission probability. We did that with COVID by making people wear masks. You can reduce the duration of contagiousness. I don't have a good COVID example for that, but I guess if you treat people in such a way that they go through the course of disease at a faster rate, or go through at least the contagiousness part of the disease course at a faster rate, you can probably reduce D. And yeah, just back to the transmission probability example, if we're thinking about just whenever there's like a complex, like convoluted web of causation, like basically, which is like what this is this giant component cause model, that's a good thing when things are that complicated, just because if each of these things is necessary, that's unlikely, but like if everything in this picture is necessary for disease to happen, you only need to change one and you break down the entire mechanism. So that's something that's nice about transmission probability, is like the more complex it becomes, the fewer, basically the more parts a machine has, the easier it is to break, that kind of thing. So effective reproductive number, something I mentioned before is that like R naught equation doesn't take into account that not everyone is susceptible. Some people are immune, some people are protected by age and sex. So yeah, this is pretty straightforward. You can calculate effective reproductive number by multiplying R naught by the proportion of people in the population that are susceptible.